Today in this video, we're going to be talking about non-right triangles, and we're going to take the conversation we've been having about law of sines and law of cosines and kind of switching gears to talk about finding the areas of non-right triangles. And I'm going to be covering two different formulas today. The first one is based off of the law of sines. So the idea here is this is going to be some sort of non-right triangle. If it was a right triangle, you would want to just go back and use the old area equals 1/2 base times height that you've used before in a geometry class. But let me do a little bit of a derivation here that involves the law of sines. Let's say we know the lengths of two sides of a triangle and the angle that's in between them. Well, this is important. It's got to be in between the two sides, a side angle side type of situation. I'm going to go ahead and put in what's called an altitude. Altitude goes from a vertex to where it's perpendicular to the other side, because then I can start to talk about different parts of it here. And I'm going to have this ratio here that the sine of the angle is to the side opposite of it. This is the law of sines. Sine of alpha is to length h as the sine of 90. This would be 90 here, is to side c. So I'm just using the law of sines, those sets and pairs of angles and sides across from them to get this particular ratio right here. Now I'm going to isolate this h is what I'm going to do here, and so that's what I did here. What happened here, the sine of 90, if you recall, is just 1, and so that's where that switched to a 1 right there. That's what that happened. So I did a little cross multiplying. Multiplied here, and I multiplied here. And then I had h times the sine of 90, which again is just 1. C times the sine of alpha. And then I divided both sides by that 1. So that's how I ended up with this expression right here, which gives me that h is equal to the length of c times the sine of alpha. Okay, I'm just going to leave that for just a second here and go to that old formula that you know from geometry. Area of a right triangle is 1/2 the base times the perpendicular height. But I know that this now can be substituted in for that right there, or set equal, excuse me, so I can substitute this in for it. And we end up with this formula right here. And this one you should put in your notes. The area of, and make sure you put this down as a non-right triangle. The area of a non-right triangle can be found if you know two sides lengths and the angle in between. And it's really, really simple. It's just 1/2 times the length of one side times the length of the second side times the sine of the angle in between. It does have to be in between them, though, or this doesn't work. So please make sure you put that as a note in your notes. Let's take a look at one really quick here. This is fairly simple to do. Again, it's 1/2 times the length of one side times the length of the other side times the sine of the angle that's in between them. There's really not much to even show here as far as algebra. You just pretty much plug it in and crank it out, and there's going to be the area of that triangle right there, a non-right triangle. All right, so that is your first formula. As long as we're talking about non-right triangles, let me show you something as far as a little trick for other things that aren't triangles to start with, but they're some sort of what's called an irregular polygon. So it's not like a nice perfect hexagon or octagon or even a rectangle or a square. Irregular, the sides aren't congruent. We can use that new formula for a situation like this. Let's say I wanted to find the area of this right here. It's not trapezoid. I mean, these angles aren't the same. It's irregular. What you can do is you can go ahead and just draw a line through it. And I could have drawn this either direction. It doesn't matter. I just put in a diagonal, of course, giving me two triangles. I could have drawn it this direction as well, and it would have worked just fine that way as well. Now you focus in on one triangle at a time, and it's 1/2 times the lengths of the two sides times the sine of the angle in between. Run it through your calculator, get the area of one part. Do the same thing here, 1/2 one side times the other side times the sine of the angle in between. And of course, then you could add those together. You'd have a total area here of 44.7. So this formula has applications to lots of irregular shapes as well, as long as you're creative and put some diagonals in to help figure those out. Okay, so that's our first formula. And again, this one is used when you know the lengths of two sides and the angle in between. Now there's another formula. This is named after a person. His name was Huron. So it's the name of it's going to be Huron's formula. And this one is not based off of the law of sines or the law of cosines. This is just another way of finding areas of non-right triangles. But this one's specific to when all you know is the lengths of the three sides. His formula is a little bit strange in that it comes in two parts. You have to do one thing, and then you're going to use that for the other thing. So you cannot just write just this part down. You have to write both parts. So this is like step number 1. You find S. Now Huron called S, what it was is you add up all three sides, the lengths of the three sides of the triangle, and divide by 2. Please note, this is not a typo. It's not the average length. It's divided by 2, not 3. Please be aware of that, or you'll be goofing this thing up. And that just tells you what some number S. And then the second step is you take the square root of that number S times the difference between S and the first side, the difference between S and the second side, and the difference between S and the third side. Again, what you know in this situation is the lengths of three sides of a non-right triangle. And that will give you the area of the triangle. Kind of an interesting formula, the fact that it comes in 2 steps. This is step part 1 and this is part 2. So I'm going to do an example here, and this one actually is a right triangle. I want to prove to you that Huron's formula works because it's such a weird formula that something in 2 parts like that. So if you want to pause it, you can actually find the area of this just by going 1/2 base times height, the old right triangle formula. It'll work. I'm going to show you that you're going to get the same number by using it. So Huron's formula can be used with any triangle as long as you know the 3 sides. I wouldn't necessarily use Huron's if I knew it was a right triangle, but I just want to show you, I want to prove to you that it works. So again, step 1, I got to figure out what S is. So I take all 3 lengths, I add them up and divide by 2. And that's going to give me a number. In this case, that number ends up being 11.1. So there's my S. Now I go to up here. I'm going to take the square root of 11.1 times 11.1 minus, and it doesn't matter which one you put in here first. We can go with that one, or that one. It doesn't really matter. I chose to write it this way. 11.1 minus 9.36, and then 11.1 minus 7.74, and then 11.1 minus 4.95. You can actually do all this in one big step in your calculator, as long as you're watching that you get all your parentheses in there correctly. And you'll end up with 19.3 square centimeters. Now again, if you thought, well, that just seemed like a bunch of mathematical hocus pocus, go ahead and pause it. Take 1/2 the base times the height, and you'll see that it's the exact same thing. So Huron's formula really does work. It just doesn't have to be for right triangles. So take this here. Again, the neat thing about Huron's formula is you can find the area of a triangle, or an irregular polygon in this case, with just measuring the lengths of sides. I don't have to know any information about angles. I can literally do it with a ruler or a tape measure. Just like the other one I showed you before, you have to be a little creative sometimes in breaking it up into triangles, and just like before, there's more than one way that I could break this up. I had to choose something. So the first thing I did is I put in this diagonal here, and I got the measure of that. It was 8.5. So I'm going to work with this triangle right there. I'm going to find the area of eventually 3 triangles, and I'm going to add them together. So again, Huron's formula, step 1. Take the 3 sides, add them together, and divide by 2. And I end up with 13.25 for my S. Then you take the square root of 13.25 times S minus the difference, or finding the difference between S and each of the lengths of the sides. I'm just finding the difference here is what I'm doing. And that turns out to be 23.9. And I just sort of repeat the process now. I break it up. Again, this time there wasn't more than one way, but the first time there would have been more than one way to do it. So now I can work with either one of these. I did the 8.5 and the 5.5 and the 4.2, so I'm finding the area of this triangle next. Find the S, and then apply the formula, and this chunk ends up being 9.8. And then this one as well. 5.5 plus 4 plus 9 divided by 2 gives me the s, and then run it through that big radical, finding the difference between that each one times the original, and we get the 7.5. So of course when I'm done now, I can just add the areas of the three triangles together to give me my total area. And that's Huron's formula. So two different formulas today. The first one does not have a name, but you use it anytime you know two sides and the angle in between of a non-right triangle. Huron's formula, you use it with non-right triangles where what you know is the lengths of the three sides, but you don't have to have any information about angles. So you will have to be able to choose on a test which one is the correct one to use. There's a few problems to practice here. Have a good day.